Only the valence electrons are considered when writing electron dot diagrams and Lewis structures. Previously, we learned the pattern of valence electrons across the families of the periodic table. So determining the number of valence electrons is as easy as identifying the column in which the element is found. I've linked to valence electrons in the periodic table video in the description below if you need a refresher. Remember, by definition, molecules are held together by covalent bonds, and covalent bonds are when atoms share a pair of electrons. So if I have two hydrogen atoms, they each have one valence electron. So I'm going to represent the valence electron for the hydrogen on the left as a blue dot, and for the hydrogen on the right, I'm going to use a green dot. These two would like to share their valence electrons between each other, but in order to show that they're sharing, I need to put both of the dots in between the hydrogen. So I'm going to move the green one over. Now I could circle the hydrogen on the left and see that it has two electrons that it can use. Its original blue electron plus the green electron that came from the other hydrogen. And if I circle the hydrogen on the right, we can see that that hydrogen also gets to use two electrons. Since hydrogen only have electrons in energy level 1, having two electrons fills that energy level and makes them stable. That shared pair of electrons is the covalent bond. Each hydrogen came with one electron. Since there's two hydrogens, we should have two electrons total, or two dots in our diagram. Sometimes it's not possible to use two different colors to differentiate between the electrons from each atom. So we could substitute other symbols in place of the dots. Here we have a dot representing the electron from one of the hydrogen, and a small X replacing a dot to represent the electron from the other hydrogen. It's still considered a dot diagram, and the two symbols, the dot and the X, are still representing a shared pair of electrons, or the covalent bond. I could also write this as a Lewis structure, where I'm going to replace the shared pair of electrons with a dash, which represents the shared pair of electrons. This can also be written as a molecular formula, H2, which also represents the two hydrogen being bonded together. Let's see how this would work between two chlorine atoms. Chlorine is in group 17 of the periodic table, so the chlorine has 7 valence electrons. That means we're going to put 7 dots around each of the chlorine atoms. Each chlorine has one single electron down at the bottom. That tells us each chlorine wants to make one bond in order to have 8 electrons available in the outer shell. The single electrons that are being shared need to be written in between the two elements. So I'm going to move this blue dot down to the bottom, and I'm going to move one of these green dots on the other chlorine. So now their single electrons are in between the letters. If we circle the chlorine on the left, we can see that it has a total of 8 valence electrons available. Its original 7 plus the 1 that it's sharing from the other chlorine. And when we circle the chlorine on the right, we see the same. It has 8 electrons available to it, 7 of its original plus 1 that it's sharing from the other chlorine. And that shared pair of electrons is the covalent bond in the molecule. We should have a total of 14 dots because each chlorine had 7 to start with, so there were 14 electrons, so we should have 14 dots. In this example, we can see that there are additional electrons that are not involved in the covalent bond. We call those unshared pairs of electrons. The electrons are still paired up, but they're only being used by one chlorine, not by both. If we were to draw the Lewis structure, we could replace the shared pair of electrons with a dash to represent the shared pair. And remember that dash represents 2 electrons. But we need a total of 14 electrons represented. So in this case, we would need to include the 6 unshared pairs of electrons as well. And those 6 unpaired shares represent 12 electrons. The dashed line represents 2 electrons. We could also write this as a molecular formula of Cl2. This also works if you have 2 different nonmetal atoms bonding together. So hydrogen is in group 1. It has 1 valence electron, so we're going to give it 1 dot. Oxygen is in group 16, so it has 6 valence electrons. It gets 6 dots. Remember, we put 1 on each side, then we go around and double up. Let's rotate the shared electrons and stack them vertically. If I circle the hydrogen, we see that it has 2 dots representing 2 valence electrons that would fill its first energy level and make it stable. All the other nonmetals need to have 8 valence electrons, or 8 dots. So when I circle this oxygen and I count up the dots, oh, I see it doesn't have 8. Right now it only has 7. It needs to make 1 more bond. It needs 1 more electron. And where is that going to come from? It would have to come from another hydrogen atom moving in to fill in that gap. Let's check our work. Each oxygen has 6 valence electrons, and each hydrogen should have 1, for a total of 8 electrons, or 8 dots. And if we count the dots around the diagram, we see that we have a total of 8, no less, no more, which is perfect. We can also write this as a Lewis structure, where we're going to replace the 2 shared pairs of electrons by using a line between the letters. So I have hydrogen with a line to oxygen, and then another line to the lower hydrogen. Now remember, the lines represent a shared pair of electrons, or 2 electrons, but we need to account for 8 electrons. So we need to make sure we include those 2 unshared pairs of electrons in the oxygen. So now when we add them up, 2, 4, 5, 6, 7, 8, we have a total of 8 electrons represented. 2 unshared pairs, 2 bonds. We could also write it as a molecular formula. In this example, we're going to show 2 oxygen atoms bonding together. Each oxygen has 6 valence electrons, so we're going to put in our 6 dots. Drawing a circle around the oxygen that's on the left-hand side, we see that it has 1, 2, 3, 4, 5, 6, 7 electrons available to it, or 7 dots. And the oxygen on the right also has 1, 2, 3, 4, 5, 6, 7 dots available to it. Now we know that both oxygen want to have 8. They each have a single electron down at the bottom that they could also share with each other. But to show they're being shared, they need to be in between the letters or in the overlapping circles. So I'm going to move those single electrons in between the 2 oxygen. Now if I count, I see 1, 2, 3, 4, 5, 6, 7, 8 electrons for the oxygen on the left, and 1, 2, 3, 4, 5, 6, 7, 8 electrons for the oxygen on the right. You'll notice in this case we have 4 dots in between the oxygen, or 2 pairs. And remember, each pair of shared electrons represents a bond. So here we've made 2 bonds, or a double bond. We can write the Lewis structure, where we replace the shared pairs of electrons with a line. So we would have an oxygen with not just 1 line, but 2 lines, because it's sharing 2 pairs of electrons. 2 lines only adds up to 4 electrons. And remember, we needed to account for 12 electrons, so we need to maintain the unshared pairs of electrons in our diagram as well. Remember, each dot represents 1 electron, and each bond represents 2. So this is 2, 4, and then we count the dots. 6, 8, 10, 12, for a total of 12 electrons. We can also write this as a molecular formula, where we just write O2, showing that the 2 oxygen are bonded together. Now let's examine how 2 nitrogen atoms could bond together. Pause the video while you try this one on your own. Then restart the video to check your work. Nitrogen is in column 15, so each of these nitrogen have 5 valence electrons. So we're going to give each of them 5 dots. Circling the nitrogen on the left, we see that it has 1, 2, 3, 4, 5, 6 electrons available to it. And the nitrogen on the right has 1, 2, 3, 4, 5, 6 electrons available to it. And we know they both want to have 8. Both nitrogen have single electrons down here at the bottom that they could share with each other. And they also have single electrons on the outside that they could share with each other. In order to show they're being shared, we need to write them in between the symbols or in the overlapping circles. So I'm going to move the ones on the bottom up in between both element symbols. And I'm going to move the ones on the outside in the middle between the two elements, again in the overlapping circles. Now if we count, we see 1, 2, 3, 4, 5, 6, 7, 8 available for the nitrogen that was on the left, and 1, 2, 3, 4, 5, 6, 7, 8 for the nitrogen that's on the right. Let's check our work. Each nitrogen has 5 valence electrons, so that's a total of 10 electrons, or 10 dots should be in our diagram. And if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 3 shared pairs of electrons between the nitrogen, or a triple bond. Now we can change this into a Lewis structure. We're going to have the nitrogen with 3 dashes between the nitrogen. That's our triple bond. Each one of those dashes represents 2 electrons. So 3 dashes equals 6 electrons. But we need a total of 10, so we're going to include the unshared pairs of electrons that each of the nitrogen has. These unshared pairs show back up in our Lewis structure. We can also write this as a molecular formula, showing the 2 nitrogen bonded together by using a subscript of 2.